in the late 1930s as equipment moved from steam-powered reciprocating motion to electric-powered rotary motion. Up until this point in time, equipment was sealed by gland or rope packing. The function of both mechanical seals and gland packing is to retain liquid product inside equipment. This prevents the product entering the motor and escaping to the atmosphere. Traditionally, gland packing was made in a basic braided hemp construction. Packings are now manufactured in materials like PTFE, graphite, and special acrylic fibres for a wide range of service conditions. Let's take a look at the pros and cons. Gland packing is inexpensive, and whilst adjustable in operation, this can be a dangerous practice. It is maintainable without dismantling the equipment, but the gland follower has to be pulled back, and removing the packing rings from within the stuffing box can be difficult. On the flip side, gland packing requires lubrication or it will burn out, so inherently there will be some leakage. Constant monitoring and adjustment is required. Adjustment is not precise, which can lead to wear of the shaft or sleeve and high power consumption. The proven alternative is mechanical seals. They provide more efficient sealing than gland packing and are available in options that do not wear the equipment. There's minimal leakage of liquid product to atmosphere and low power consumption. When the correct mechanical seal is installed, you can expect many years of maintenance-free performance. So here we have a cutaway of a typical mechanical seal. The seal is composed of two basic parts, a rotating component and a stationary component. The rotating component mounts to the rotating shaft of the equipment, and the stationary component is fitted to the stationary housing. Most seals are mounted internally, with liquid pressure closing the seal faces in combination with the seal spring force pushing towards the stationary component. This prevents liquid escaping when the correct seal type is installed. Here are some ways to actually identify mechanical seals. Firstly, they can be identified by seal size. The shaft or sleeve is measured at the point where the rotating component is fitted. Secondly, by spring type. A seal that is energized by springs is usually a single coil spring, a single wave spring, or a multi-spring design. Thirdly, mechanical seals can be identified by the secondary sealing component as shown by the three examples here. And finally, mechanical seals are identified via the material of the seal mating faces. Seal faces are manufactured in materials including different grades of carbon, ceramic, tungsten and silicon carbides, and metallic materials. Here we see some of the different types of seals available. You will note that both single and multi-spring seals can be manufactured in a multitude of different seal designs and arrangements. Let's take a look at the two components to a mechanical seal. Firstly, we have a rotating component. The complete rotating assembly consists of the face, retainer or seal housing, spring or springs, and a secondary seal such as an O-ring or wedge. Secondly, we have a stationary component. Types of stationaries used are O-ring mounted, which uses an O-ring to seal in the housing recess, rubber cup mount, or a clamped-in gasket type. So what materials are actually used in seal construction? Some of the materials include stainless steels, carbons, carbides, PTFE and plastics. Secondary sealing components are typically made from an elastomer, PTFE or graphite material depending on the sealed product. Seal hardware comprises of parts such as seal bodies, springs and housings and are usually made from